Okay, welcome back everyone. So a little bit about, we're going to proceed. Now we're going to have another talk using embeddings and deep neural networks for demand forecasting. And after that we have, so far as I know, one lightning talk. If you have another lightning talk, now is the time to notify us. And yes, after the lightning talks, we will end the streaming for everyone who joined online, and we can, after lightning talks, we can have more beers downstairs. They will be there at the same place where we just had the pizza, and we can just have some more drinks and chat and network. And so, yeah, please a warm welcome to Daniel and Martin.
Thank you. Thank you for having us. So I'll start a bit with some background. So Martin and myself both studied physics and are more than 10 years part of Blue Yonder. Blue Yonder, for everyone to know, is a supply chain software company. So you see here the biggest pillars of things that the company is doing in supply chain software, and we are working in demand planning segment, and there especially on Luminate Demand Edge, the latest demand forecasting engine that the company has. So Luminate Demand Edge is a probabilistic demand forecasting engine which works for our customers, which are usually retailers, grocers, or other manufacturers or other goods that they are selling to their customers, and they give us the data. We cross-correlate that, use our algorithm, so we will come to the algorithmic part in a minute, and then we output a probability density function, not just a point mean regression estimate, but the whole density function, which then allows the further algorithms to optimize on cost functions. For example, I don't know, if you are selling vegetables, how much do you order that it's not perishing too much and that people are not sitting in your store and are not having broccoli any longer. So that's the typical use case. So a very brief overview on the history, what we used. So basically, we had a first algorithm called Neurobase, was founded in the 90s, was a physics collaboration because the founder of the company, a physics professor, did that together with his colleagues in CERN. And then in 2013, we basically changed from the very broad Neurobase to an open sourced algorithm cyclic boosting, which we developed in-house and open sourced later, and which is basically able, when you focus on specific data sets, that you can define very clear interactions, and which allows you to model data problems very specifically and very rigidly, and has there its advantages. So everyone welcome to look at that on GitHub. In 21, we released an update that we were building for some time before that, that allowed us to go back from local, so basically in-memory calculation, to what we call global, so basically on the whole data set at once, which was necessary because we had bigger and bigger customers and thus needed something to scale out. And the latest addition, which the talk is basically about, is what we call then DeepMeta learning. It's also a global principle where we will see in the talk what that means about. And we have some ideas already for the future, what will come after that. So why already 2 years later something new? So basically, it's not only about technical performance, but rather on scaling out to more and more customers. So like if the feature engineering that is still required in our current ansatz is basically limiting the speed with which we can bring in new customers which have different data sets. And basically that's also like what Gail talked about in the previous talk, that you need something to represent how the data looks like. So, and basically that's where our current ansatz comes in. We might be looking at transformers in the future. So for the next part, Martin will come up and talk about what we basically did in the engineering to work on that ansatz.
Yeah, hi, and thanks for the introduction, Daniel. Yeah, I will talk a bit about the model that we currently are taking live or having live for our customers. So, as Daniel mentioned, we have several columns that the model needs to take into account, like the product identification code, the brand of the product groups, and these are just a few. So we also have weather data, location data, promotional data, price data, and so on. And one thing that our customers want is interpretability of the prediction. So you see that our demand forecast is a sum of different factors. And these factors map more or less to the input features. So the promo factor gives you an indication how the demand varies with promotional changes, so if the product is in promotion or not. And what we now have is, so we plug in our raw features that I just mentioned, and the DeepMeta learning does then learn representations of these inputs. For example, out of all these product influences or product features, we learn product meta features, and these are then combined in the connectors to have interactions with, for example, with promotions or so on. So this is before, in the generalized additive model that Daniel mentioned, we had to write down all the features and all the interactions manually. So not like in a decision tree or so, where you also can plug in everything. We had a model where we had to write down everything. And this was suboptimal and did also not scale well across the customer base. So this is now like the architecture, how the architecture looks like. I mentioned these influence categories, and therefore we kind of have, here we said, okay, let's focus on three feature types. We have product features, location features, and seasonal features or calendar features. And since we want to provide also these influence categories at the end, we have three streams that kind of are very similar. So if I take the product features, for example, you see that we have categorical features like the product ID, the brand, and so on. These are put into embeddings. So and the continuous features are more or less normalized and also cleansed for missing values. This then goes into an MLP. We call this the meta learner. And here at the end of the meta learner, so it's just a multi-layer perceptron. At the end of the meta learner, we have several outputs. And these outputs we call then the meta features. And this is then the product-specific part of our prediction. And after that, we have another stage called the connector stage, where we now combine different meta learner features. So for example, if you consider the seasonal feature, this would be day of week, day of year, stuff like this. this we want to combine, for example, here with location influences like the region, the country, and so on. But instead of doing this on a column basis and writing down these interactions, we now just combine the meta features. So this is done just by concatenation, the feature vectors, and then putting it into another MLP. So that's the role of the connector. And these connectors normally have one output. Here the seasonal connector has two outputs, but this is, I think, outdated. And these outputs then comprise our factors. And as you saw on the previous slides, the prediction that we put out is the mean prediction and the variance prediction. And this is just the sum of the logarithmic output nodes here. And this is also what we then provide for our customers in the UI. So they get a prediction, they get a variance band around it, and also all these influence categories. So this is now an example. So we have not really, we need really interpretability. And as you see here, we have an old model that more or less is the GAM model in orange, and a new model that's the blue model, and the prediction across the time. And you see here that in light orange, here are all these influence categories. And you see, for example, that the event factor rises here and goes down, no? And then it rises again and goes down. And this is the prediction for a product that never saw Halloween or Christmas ever. So the model really generalized this event effect, as you see here in the upper main plot, whereas the old model did not really learn that very well. So it had just a product group approximation of how Christmas looks like. So the customers can then really see, okay, what's driving this prediction here in this time range? It's the event factor. So it has to do with events like Halloween, Christmas, and so on. And that's what they want. They don't really want just a black box. So in here you see a bit how a meta learner can learn and automatically, since our data is quite diverse. So you have a temperature column here, a float column, and then you have an ID column, like you would have 100 products with numbers 1 to 100. We plug every categorical feature into an embedding matrix, and by the optimization, so we do stochastic gradient descent on mini batches. By the optimization algorithm, the information about the sales, so you see that there is one temperature dependence that is going down, the other temperature dependence is going up. And here you see how the model kind of finds this out during the optimization automatically. So you don't need to kind of guess what would be winter products or what would be summer products or so. This is kind of done for you. Also the mapping, that the ID and the float column are important. Another example would be our location information. Here we are looking at the region in Canada. So, and this can then more or less, what the embedding does is, and the meta learner then itself, it's mapping the region information into another space. No? So for the retail business, it seems that it's kind of important to know that some subregions have many coastal areas and the others might not. So it's more or less an example, but we can also plot these meta features and go into lower representations. And then we see such things that patterns like this are learned. So now the quality of the new model and the complexity. So at the right-hand side, you see kind of different state-of-the-art machine learning models from different, for different use cases like text processing or language model and image models and so on. And our old model had quite a lot of parameters, and we went a bit down now since we are now many more parameters in the model are now shared. So we don't add an interaction, for example, for every product we need a dependence to the temperature. This we don't really do. The model finds out where this dependence is needed. So we have lower parameters than before. The forecast accuracy is better, so we could also not find underfitting that more or less is stuff that we checked with all these time series plots, that really the effects are also described. And here in this matrix, you see on the rows, you see all our customers, and in the columns, you see prediction metrics like MSE, mean deviation, MAD, and you see the differences, and these are quite green, which means that the new model was better than the old one. And this is also the procedure how we take changes live. No? We do for every customer cross-validations across several years, and then measure the KPIs and look at time series plots. Another funny thing, we were on the PyCon in Berlin this year, and there the team around Felix Wick, they did a hackathon to beat a simulated data set, which is kind of like our real retail data. And you see that we are on place 3. So without a lot of feature engineering, the cyclic boosting master submission was even better, and also 2 other candidates. But the master submission also was hand-tuned. So there were interactions were written down, and a lot of pre-processing of the data was done. Whereas we kind of just ran this off-the-shelf method that we have at the moment. I think the first one was the tabular learner from OpenAI. That's also quite powerful. And now I would hand over to Daniel again.
Thanks, Martin. So, I mean, we talked about now how the architecture looks like, and I now come to the challenges that we were facing, basically putting something like that into production. So to give you some context, this is the number of product location combinations that we have for customers. So we have some customers with several thousand, but lots of customers with several million of product location combinations. Now multiply that with several years. You come to the billions. So we have more than 300 billion rows in the combined data set. And that basically, as this steers the daily business, so about how much salad and how much tomatoes are in the supermarkets and other things, this is very sensitive in not doing errors, in like we cannot order 20 million tomatoes in or whatever, then the businesses would go bankrupt. So we have a quite dedicated quality workflow to check that things are working fine. The first part, I mean, everyone has, or at least says so, so static code checks and test coverage. But what we have in addition, which was crucial for us, is a model change detection test. So we have a minimalistic data set for each of our customers that is sufficient to detect if any refactoring or any change steers something that could change the model. So basically that you just want to performance optimize something, and you do a bug inside and create a problem. So this is basically there to protect us against such things. And when that layer basically succeeds and we find, okay, there was a model change, or I mean, normally we do that on purpose. So we change things to go into something. Then we are going for the full model evaluation pipeline. And the model evaluation pipeline is run for every customer on a respective data set with at least 100 million rows, so to say. I mean, if the customer has so many. And this basically has done multiple trainings that are time cross-validated and evaluated on multiple horizons, because the different horizons are important for the different ordering decisions that are happening afterwards. And we save everything from prediction quality metrics and runtime metrics into MLflow to have an overview and can basically look on everything at once. So the first thing that we encountered were basically the costs, the performance changes. So basically on start, I think on start we were a factor of 400 or so slower, but then at the end a factor of 10 slower in training time compared to our previous model. And then basically started using GPUs, which we hadn't done so far, and basically could bring it down with GPUs to an identical training time. We are running on Azure, so basically everything has to be booked on Azure, and there the GPUs that we were using were a factor of 7 more expensive than the CPUs, and there we optimized further in how we are booking the training machines, so like from the usage patterns, and came down. So I think in the end we were a factor 1.7 more expensive, but that was fine for the overall cost structure, as the training is not the most critical part in that. So that one was fixed, and then to the quality, I think Martin showed the overview graph where everything looked green. And I also wanted to basically give a quick overview on what we are doing. So we have multiple overview plots on all customers. So we had these influencing categories here. On the upper right side, I depict the price change, so we can basically see how our distribution among customers changed with different model versions, and basically see patterns there. We have that for all the influencing categories. We have that also for basically all the overview KPIs. And in addition, we store several hundred individual time series plots on the individual products and locations that we are predicting, so that we can look at the worst MSE, the worst MAD, the worst whatever KPI we want to have, and see, okay, do we find outliers? Do we have made any problems with that? And basically have that saved all together so that we can compare different model runs at once. So from the whole timeline, we basically started last of October with the initial implementation and had then a full feasibility check around Christmas last year. And then I think a major part we are having feature completeness. So we basically, some of the more complex things we did not integrate in the feasibility check, like our cannibalization model, but then added later. And then the technical challenges with the runtime that we solved in April. And we have already gone live with the first 3 customers, and will onboard the next until end of September, so that we are full at all the 30 customers or 32 or whatever that we have currently. So what can basically be the outlook and the further extensions? So I mean, the main goal was that we can go into different areas, because we can now easily extend to additional data attributes. We could also integrate text, image, or item data. So basically also in the direction from the previous talk, how can I integrate data sources that are basically available and are not structured as we define from input side. And then we also want to experiment on sequence-to-sequence transformer models for further optimization. Yeah, that's so far for the outlook. Thanks for your attention. And if you find it interesting, you can come on in a talk with us.
Thank you. Interesting talk. I have to ask, it's kind of a silly question, but did you challenge your model by going to Australia, so to the other side of the world, with the seasonality and the location?
So we try to be independent of that. So basically, we get weather data from an additional provider, and we try to learn how is the seasonal pattern, and then have that attributed. So like that's not like winter is always in April or what for Australia, but that should be learned from the data.
Yeah, but initially we did. So initially we had the first customer.
We're all on the Northern Hemisphere and no one thought about it. Yes, that's right. But that was a couple of years back, we got the first South African customer, and since then we have it.
One comment, that's not a global model, right? So it's not one training for all customers.
Not for all customers at once. No, for privacy reasons, the data is not shared. So that's one.
No, the global means that we use all the data of one customer, since it's already quite large, as you saw maybe in the number of PL combinations that we showed. This before, so in cyclic boosting 2013, we did train on product group location partitions more or less, and had several thousand fits then and independent models.
Thanks for the talk, very exciting. How does the model handle the cold start problem? Does it need a demand history for a certain product, or can it do predictions for completely new products, like in fashion, for instance, if something is completely new on the market?
It can do also predictions for completely new products. I mean, it's more a challenge because, I mean, if you have like a couple of days of sales history, you very well can anchor the overall pattern. Is it like selling 5 times a day, or is it selling like 5 times a year? A year you don't catch in that short time frame. But what we try, and I think that's also the main benefit of the next approach, is that we learn from additional product attributes like color, size, whatever, how those products might behave, and yeah, and I think that's also I don't think we have it on the slides, but 70% of the new lines that we are predicting have improved in our metrics for our customers. So there was a huge benefit with introducing these embedding layers for the new lines.
Yeah, so for normal customer, we integrate historical data deliveries. But if they have dynamic assortment, that's not really big of a problem. We have a static prediction from the machine learning part, and then once the sales kick in, we also correct in this prediction again.
So, thank you for the nice talk. I have a simple question, maybe. Is there a conceptual difference between explainability and interpretability of a model?
I
mean, the explainability we need is more or less in the output. So when we deliver the prediction to the customer and he sees it in our UI, and then he might also be an expert in his sector, so he is surprised, or he says, wow, that's a good prediction, or he says that might be too large, or why does the prediction go up by a factor of 2? He has then normally 2 options. Rather he believes the prediction, or he puts in a prediction override. And to do this in an educated fashion, he can look at the demand factors and sees, okay, there's a promotion going on, the price is reduced 30%. That might be the same order of magnitude that I saw in the history in similar situations. And then for this we kind of try to provide not only the prediction point forecast, but also these the inputs we show the customer again, the prices, but also the price factors the model learned.
And then to add, your question was very specific on is this explainable or is it interpretable? And I think...
Was a reference to the last talk.
Yeah, exactly. And I think Martin also mentioned that the main part is that we want to group it by input sectors of the input data so that you know which data source has changed and that's driving the prediction. But it's not like, I mean, in the end we have like 10 categories or so. So in the end, and we have like several hundred influencing factors beneath. So it's a simplification, and it's not like giving you the whole explanation. You have to understand much more and have to basically look at the whole time series to understand what's going on.
Yeah, thanks for the talk. Related to the question of the gentleman in the white polo shirt there, have you thought about using your model for product design questions? Like if you can, for instance, predict that a new piece of fashion in color red and size whatever is going to sell more often, would you be able to use it for recommending new products and their features?
Yeah. So we haven't done this yet, but I think it's on the first side. So you have promotional planning. So that would be when you do promotions. You mentioned how would a piece of clothes sell maybe in the next season. It's at the moment it's just not live there, but I think the capabilities in terms of machine learning you would have, but you could do it in a similar way, but I would then call this a different product, especially if you have text and image information for clothes, you might be able to do that. On the other hand, if you're thinking about the quick fashion, the fast fashion sector, it's also not so easy to predict, I think, but yeah, could be done, I think.
Especially when adding that the type of, I mean, you have, usually we have, for example, colors as attribute, and we have like 30,000 colors for one customer, because like they are not normalized in any sort of way, and they are completely different. And sizes is the same thing. You have different sizes for shoes and for trousers and for women and for kids and for whatever. And so basically that's really hard to combine.
So maybe for color it's hard, but the question is really going from demand forecasting to demand shaping. And there it becomes very interesting for our customers. So how should they change certain prices or certain promotions to drive the demand to a target that they want to achieve? And there this information is very important.
Hi, thank you very much for sharing your insights. I have a question. I want to understand better in which context you use your demand prediction model, and especially if you use it in the context of very frequent production cycles, like for example, you have a retail store which sells grocery, and the order has to be made day by day.
Yes.
And there is a low margin industry where the mistake is very costly. Like for example, again, retail grocery sales.
Exactly. That's where we are coming from. So basically, that's where the solution started. And I think the key part was on slide 2 with the probability density function, because I mean, how many what is perishable? How many bananas you sell tomorrow? Because you cannot keep them for as long. You need to know, but if you would only have a point estimate like 5, then the optimization itself cannot be perfect, because it would be limited in the cost function. So like the cost for waste is not linear, and the cost for out of stock or lost sale is not linear. And so you can much better optimize that if you have a realistic distribution. And I think that was the key element back in the days, and which we are applying every day.
So we're really in this fast sector. So we're doing daily predictions, daily data delivery in a SaaS fashion from the customer of the sales, and forecasts then up to 21 days or 1 year into the future. And the order horizon of the customers might be between 3 and 21 days, where they use the prediction to then steer their order.
And do you know, do they use a human in the ordering loop, or they use
They use human less and less the faster it gets.
So it's really hard.
Because I mean, sometimes they think like, okay, this is 6 weeks out, and I know it better. But in the super fast business, basically, there is, I mean, only in exceptional cases. So sometimes things are wrong and so on. But besides that, there should be no human interaction.
And the human interaction moves to the strategic level. That for assortment, you make the decision: do you want to risk more waste or more out of stock? So that's the human interaction. Everything below gets more and more automated, and it's just everyday.
So they use our UI then also to look at the predictions, and then in under rare circumstances they then do prediction overrides also. But the ordering is really automated then, yes.
Yeah, thank you very much for the talk. Please give a big applause.